All right, here we are with batteries. In order to understand batteries, we have to realize that batteries create electricity from atoms. It'll be our job in this chapter to see who is the giver of electrons and who's the taker of electrons. So if you're giving electrons, you're losing them, that's a Leo. If you're taking electrons, you're gaining them, that's a Gur, that's a redox kind of process. So galvanic cell is just a fancy name for a battery. It has a wire that transfers electrons from one side to the other. What you saw at the bottom of that previous page was a salt bridge. A salt bridge completes the circuit. It allows charge balance on both sides of the battery so that we don't have too much positive charge. If we have too much positive cations being formed, you're never going to keep losing electrons. They're going to stop. If we get too negative on the other side of the battery, we're going to have the same issue where electrons are going to stop going to that side because it's already too negative. So if we have a spectator ion full of, a salt bridge full of spectator ions, that means we can prevent the buildup of charge so we can continue the transfer of electrons. The electrodes themselves are the metal strips. Sometimes they are part of the battery, sometimes they're just a conductor from the solution. So it really just depends on the situation, but they're the ones that are basically touching your device, giving it electrons, to power your flashlight, to power your watch, to power your cell phone or whatever. So notice here we have kind of a test tube battery. You'll notice a few things happening here. We have on the left side zinc. In this situation, we have zinc metal, which is this strip here. And notice the deterioration at the bottom. That's because the zinc atoms themselves are losing their electrons. That's a Leo. And when they do so, they become +2 ions. So in order for zinc to become zinc +2, it has to lose 2 electrons. That's exactly what a Leo represents. Copper over here has copper metal. It already has that electrode. So copper electrode here is just being a conductive, rod or strip in this case, so that we can collect more copper. So you can look at the bottom of this electrode here and notice it's getting fatter. That's because this blue copper solution is taking the electrons from zinc, and when they're given to copper, it becomes a new copper metal atom. No charge. So as the 2 electrons here were lost, notice copper gains them. And gain is a Gur. And that's exactly what we want, is both, right? So the trick to any device then is if we plug in, say, a light bulb here, the electrons will go in, they'll light the light bulb, and then they'll go out. So in chemistry, we just cut the wire, use the electrons on their way to the other side of the battery. The problem is when all the electrons leave this side, the battery dies. So you can imagine there's 2 ways to kill any battery. So in this situation, if you want to kill the battery itself, you can imagine that when the zinc is gone, the battery's dead. You can also imagine when this blue solution is gone, that means the copper +2 is gone. That means there's no more atoms to gain electrons. So then the battery dies. So either the blue's gone or the zinc's gone. If the zinc's gone, that just means there's nobody to give. And if the blue solution's gone, that means there's no more copper ions to gain. And when either one of those runs out, the battery dies. And that's what happens all the time. This battery just doesn't happen to be rechargeable. We also notice that in the bottom of this battery, it's connected. And then in that salt bridge, we have ions going both ways. So what you'll notice about this left side is that negative ions are coming over because positive ions are being formed, and then therefore it's neutral. So zinc can continue to give negative electrons away as long as negative replaces it, in this case, a sulfate spectator ion. As the electrons go to the other side, we're losing copper plus ions because they're becoming copper. So as zinc becomes zinc plus 2, copper plus 2 is becoming copper, and unfortunately, if we lose positive, something has to replace it. So by the salt bridge allowing plus ions to come over and replace copper, it's unfortunately a 2-for-1 situation, but it keeps it from becoming negative because those sulfates are still there. So as the sulfates migrate this way, the sodium ions migrate this way, and the battery continues because no charge is built up in the end. So in a standard battery, the exact same thing happens, but with different atoms. In this case, we do have zinc. Zinc is going to plus 2. So if zinc is going from 0 to a plus 2, that means it's zinc going to zinc plus 2 with 2 electrons. That's the half reaction. If you're giving 2 electrons, you're the Leo. So you're oxidized and the reducing agent. Manganese goes from a plus 4 to a plus 3. So if manganese is a plus 4 going to a plus 3, it must have gained electrons in order to do that. That's a GUR, and that's reduced in the oxidizing agent, just like we saw earlier in the other video. So you have a loser and you have a gainer. These batteries are important because these are the batteries that you use on a regular basis. These are the Energizer, the Duracell, the Rayovac, the Dollar General kinds of batteries. And they have a manganese dioxide paste, which is kind of a grayish black paste, kind of dark brown. It's around a graphite core. And then we have this ammonium chloride and zinc chloride paste, which is white. And this zinc metal can. So if you remember back to the previous slide, zinc disintegrates as it gives off its electrons to become zinc positive 2. So as zinc disintegrates, there's going to be holes in the battery. And if there's holes in the battery, you can imagine that if we have a cartoon battery and we start getting holes in it, out leaks some ammonium chloride and zinc chloride paste. So a lot of times your parents, and your grandparents in their infinite wisdom of battery chemistry say, don't touch that battery that's in that remote control or in that child's toy, in that old flashlight, because what comes out is battery acid. Well, here's the ingredients to the battery. We have manganese dioxide, we have ammonium chloride, we have zinc chloride, and we have zinc metal. There's no battery acid in these dry cell batteries, hence the name dry cell. It's just a bunch of pastes. But it is true that when zinc gets severely oxidized, it's going to permeate a lot of those pastes outside of that little plastic wrapper. And they tend to leak around this little plastic shell that houses the zinc can. So really what you're seeing when those old batteries are getting crusty in your old toys or remotes or flashlights or whatever is these pastes escaping through those little pores that zinc created as it was being oxidized. What you'll also notice about batteries is there's always a positive and a negative. And if you've ever had to jump a car, you definitely don't want to put, you don't want to cross those, because what happens is when you cross those, you're going to get electrons that are being given to ones that are being taken, and then they can spark, they can collide, so to speak. So what we call an anode is kind of like an anion. So same kind of word, same kind of definition. Anode, anion, those are negative. Cathode, we said positive looks like the letter T. That's like a cation. So those definitions are very similar, but they're different in how they're used. So zinc in the battery said it goes to zinc positive 2, and it produces 2 electrons. If you're producing electrons, if you're losing electrons, you're going to become negative, and that's what we're seeing. Over here we had manganese +4 go to manganese +3 by gaining electrons. So if electrons are coming in, it's because you're already positive, therefore you're going to be positive on the battery. And that's a gain. So long story short, anodes are going to be negative electrodes. This is where oxidation occurs, because oxidation is where loss of electrons occurs. That's the Leo. Cathodes are going to be positive electrodes. This is where reduction occurs, but reduction is where we gain electrons, and the only way we're going to gain electrons is if we're already positive, hence the positive side of the battery. As we get to rechargeable batteries, it's a little bit fancier because now the can itself is not part of the reaction. Lithium ions are one of the best losers of electrons at the top of our activity series. And the reason this is reversible is because we have layers where we can shuttle electrons back and forth. In this case, between lithium and cobalt. So as we separate these layers, we have the ability to discharge, where lithium gives up its electrons, and oxidation. Cobalt is reduced. It goes from a +4 to a +3. The only way to lose positive is to gain negative, and that negative is coming from lithium. This lithium-cobalt complex is formed, and then all we have to do is recharge that complex back to its original state. So a couple myths about batteries is discharge them to 0, recharge them to 100. That is true, because as your electrons go in one direction, as they go in this direction to the complex, they're giving off electrons. But if you imagine that this battery is plugged into the wall, you're going to send electrons back the other direction to try to reverse this process. When you plug it in, there's a chance that those electrons, just like crossing accident cables when you're trying to jump another car and its battery, you're going to clog some of those channels because they're kind of weld themselves shut. So the more that you recharge your phone when it's not completely dead, the more you're going to kind of cram and eliminate this process of electrons trying to go both ways at the same time. So if you're using electrons that are trying to be used at the same time, you're going to slam them together. And when that happens, your battery is going to lose its ability to be charged and discharged. And this is why batteries over a 2-year period might have, a fraction of the time that they need before they need to be recharged. So when you buy a new cell phone, it might last for, 2-3 days before you need to recharge it. But even as little as 6 months, you can imagine now you have to charge it 2-3 times a day just to keep it going, to keep it topped off. And that's because you've been clogging these little channels between this lithium cobalt complex and the lithium ions themselves. And the more little holes you clog, the less ability your battery has of being recharged quickly, and the shorter life it's going to have as a result. You've probably also seen lots of videos where somebody hits it with a hammer and it explodes, and that is true. Lithium metal is very reactive with moisture in the air, and it can catch on fire and be very dangerous. So even though they are vented, they're preventing oxygen, they're preventing moisture from coming into that battery because it is dangerous with that lithium metal in its raw elemental form. It's also true that chemical reactions are temperature dependent. So you can imagine that the process of lithium discharging its electrons is based on temperature. So if you leave your phone in the car over the summer, your car gets very hot, your battery's going to die very fast. But it's also true that if it's in your car in the winter and it's very cold, it's going to last for a very long time. So some people even put their batteries into the freezer or the refrigerator, and that's because they do have an expiration date. Regardless of whether you use them or not, batteries will continue to do their chemical reaction. Our job is just to make sure we take advantage of those electrons as they're being transferred. So it is true that freezing your batteries does have some benefits. It's going to make them last a little bit longer. We can also see that cars can run on water. The reason that cars can run on water is through this battery kind of fuel cell. So you can imagine that if you put water into your tank, water can be electrified into its elements, and those two elements are fuel. So as hydrogen turns into H+, that's a loss of electrons. As oxygen turns into -2, it's gaining electrons, and that's a Leo-Gur kind of process. The disadvantage of a fuel cell in the real world is hydrogen gas and oxygen gas are explosive. So if you hit a pothole, you don't have a leak in your tank, you have an explosion. So instead of dripping gasoline on the pavement that evaporates, now you have a bomb traveling at a high speed down the road. So until they can make hydrogen and oxygen tanks safe, it's going to be unlikely that we can run cars safely on water on highways. They're just going to be stuck in these closed tracks to prove that it is possible, just unsafe in its current level of engineering. We also talked about the activity series. The activity series is kind of a revisit from the last chapter. What's most important in this chapter is to realize two features, and that's that if you're at the top, you're the most active because you lose electrons the easiest. If you lose electrons the easiest, that means you're going to be the best Leo, the best at oxidation. And if you're the best at being oxidized because you're the best at losing electrons, you're going to be the best reducing agent. So that's up. You can imagine going down, you're going to lose electrons the least easy. So if you're going to lose the least easy, that just means you're going to gain the best. So this is going to be the Gurs. And if you're a Gur, you're going to be probably a positive ion in this lower category. But those are the ones that are reduced, and those are the ones that are better oxidizing agents. So as we look at the activity series, just remember that we want to replace with somebody higher. So the hardest part about this for students is, how do you know who to pick first? Well, if aluminum has a +3, that means it has some kind of negative ion. Could be -1, 2, 3, doesn't matter. Could be all kinds of different atoms, doesn't matter. Those are spectators. What is important is if you have a charge, you're in some kind of partnership. That's the married couple. So you choose this one first, and then you look for this one second. If it's higher, the reaction works. If it's lower, it doesn't. So in this situation, aluminum is already higher than zinc, so this will be a no reaction. There'd be no reason to trade aluminum for zinc. If we use our analogy of cheating, you don't want to leave your husband or wife or your partner for somebody that is, less off. Maybe they don't have a house or job or who knows what, right? The activity series also works for the halogens. We mentioned this. The bigger the halogen, the worse the partner. So if you're higher, a smaller halogen, you're going to be more readily attracting electrons because you're going to be more electronegative. So you always want to marry up in single replacement reactions. Whether that's halogens or metals, doesn't matter. A couple more ideas that are similar to the Leo-Gur process is rust. Rust is iron and oxygen. One of the urban legends about rust is that salt in the wintertime causes rust. If that were the case, then sodium would be lower in the activity series than iron, and it's not. So because sodium is much, much higher, there's no reason for sodium ions to replace themselves with iron ions, because if you're married to sodium already, as salt is sodium chloride, there's no reason to react with metal on a car fender ever. But it is true that salt can create water at a time of the year when water is typically frozen, and that water can catalyze the oxidation process of iron, because it's iron and oxygen that make rust, and water just helps in that process by acting as kind of a weak acid. Other metals that are even more active, think water is an acid. Iron is just on that borderline kind of scenario. So here iron is 0, goes to +3. If you go to a more positive charge, you're going to be a Leo. That's going to be oxidized. And the reducing agent, oxygen, is gaining electrons from iron. That makes it reduce, but it makes oxygen one of the best oxidizing agents, and that's why you see so much corrosion with oxygen. A famous version of corrosion is the Statue of Liberty. We saw that picture before. With all the pollution, copper, even though it is very inactive, will oxidize just like an old penny over time. And when it oxidizes to +2, it's attached to iron in the inside of its statue. And in 1984, they had to spend over $39 million restoring the Statue of Liberty because the iron sacrificed itself for that copper skin of Lady Liberty. So as we lost our nice golden statue and now have this green copper statue, it's all because of oxygen and because of all that acid rain from the pollution of New York City that this happened. That sacrificial metal that we saw, in this case iron for copper, is exactly what they do for other things in the world. So you can imagine that those big iron poles that carry our electricity should rust over time and should have to be replaced. But if you attach to those iron poles a more active metal, it's easier for power companies like American to go and replace the magnesium so that they don't have to replace the steel. So because they attached magnesium, which is higher on the activity series, it oxidizes so iron doesn't have to. The same thing is on large cruise ships and large sea vessels. If they're made of iron, they're going to want to rust in the ocean, not because of the salt, but because of the water and the oxygen. So if you don't want your steel ship to rust as fast, you can bolt on magnesium plates so that divers can go down and change those magnesium plates every year or two instead of replacing the entire ship's hull. Aluminum's even better. It likes to oxidize just like iron, but if we attach a little magnesium chunk, it's usually down here right below the water surface, a little gray block. That's called a sacrificial anode, and it too will oxidize so that your aluminum boat motor, or your aluminum boat for that matter, doesn't have to. So even on car engines, you have these little chunks of magnesium that prevent oxidation because it's easier for the magnesium to oxidize, being a more active metal, being higher on that list. So if magnesium's up here, you can have any metal down here be safe because as soon as this one tries to oxidize, this one will instead. And that's the purpose of a sacrificial metal, a sacrificial anode. And that's it. So a lot of oxidation, a lot of Leo gear to look forward to. Catch you next time.